Hi, and welcome back. We're going to learn more today about weathering, and we've already discussed the physical components of physical weathering. Today we're going to look at how rocks can change and break down chemically. So let's go back and look at what is chemical weathering. Well, chemical weathering is when rocks are broken down, but also the chemical composition of that rock changes. And we'll see examples of this. There's two or three different types. One is oxidation. Now, this is when oxygen from the air combines with the minerals inside that rock, and it actually oxidizes. And we know this commonly as rust. You've seen it on the sides of buildings, you've seen it in many different areas, but rust is an example of chemical weathering. Red sand has been oxidized. And we have oxidation of the Statue of Liberty. Now, the oxidation of copper is what gives the Statue of Liberty that green look. This picture on the left side is what it was originally when it was first brought here from France. It was copper, and it is copper. But over time, the exposure to the air and to the elements has led to oxidation, and it creates this greenish color that we call patina. Now here in this picture is the eagle. In the statue on the left, it's like a newer statue just made of copper, and it ages over time, not ages, but it oxidizes over time. So it gets to be that greenish color. The second type of chemical weathering, is called carbonation. And this occurs when water containing carbonic acid dissolves minerals in the rock. And the example of this is limestone caves. Now, these caves are literally created by water seeping into those cracks in the rock, and it actually eats away at the limestone, and it changes and dissolves that. It actually changes the chemical composition within that rock, and it leaves behind these larger spaces, or like the broken down rock. So we have caves that are forming. And here we have a picture of the step-by-step process where the carbonic acid will seep in to the limestone, and then it eats away and it dissolves that limestone, changing it chemically. And that creates these larger gaps or these formations, which are known as caves. You may have been to Howe Caverns in upstate New York. This is an example of a limestone cave that has been created through carbonation. And here's a picture of caves inside, and you see the really cool formation from carbonic acid. Actually, it's created stalactites and stalagmites. Stalagmites grow from the ground up, and stalactites grow from the ceiling or the top of the cave and grow downwards. It's pretty cool. Granite is intensely weathered, and it almost looks like Swiss cheese with the holes, right? All through carbonation. Another way the rocks can be broken down chemically is through pollution that we've created and put into the air. We have the oxides of sulfur and nitrogen make rainwater unnaturally acidic. So as the pollution is in the air and as the water droplet forms around the condensation nuclei in the air, which is pollution, it creates an acidic rain or acid rain. And this is the pH scale, which is what helps us to determine how acidic or how basic a substance is. And acid would be on the lower end of this range. Here's a picture of acid rain that damaged this forest in Germany. Now, there are some effects on human life because of acid rain. It breaks down toxic metals held in the ground, and it frees them up, and they wash into water sources. So sometimes we need to be aware of that so that we don't drink the groundwater if it's affected by the acid rain, or we don't swim in it. As the water becomes more acidic, it could react with lead and copper and water pipes, and that could contaminate drinking water if the pipes that you're using to get your water to your house are made by copper or copper pipes. And in Sweden, the drinking water became so contaminated once that it turned their hair green. Hopefully that won't happen to us. Now, there are certain climatic effects on weathering, and we'll notice that the differences when we go through it. Physical weathering will occur mostly in cold, moist climates. And this kind of makes sense because if you remember back, physical weathering can be in the form of frost action, right? Where the water freezes and thaws, and that really can only be in areas that are cold and moist. So that makes sense, right? Well, chemical weathering also occurs where it's moist, but it also will dominate in warmer regions. So that's where we see the carbonic acid and the oxidation occurring. Now, what do they both have in common? Well, mostly weathering will occur where there is moisture. And the more moisture there is, the more weathering that will occur, whether it's physical or chemical. Picture of Cleopatra's Needle. It's a landmark, and you can see that over time its exposure to weathering has caused it to be much less detailed in its carvings and its inscription as it was when it first was placed. Now we have a picture here of weathered tombstones, and we're going to talk a lot more about that in class, but tombstones are usually a really good indicator to scientists who are studying weathering and the rates of weathering in certain areas, because tombstones are stationary in one location and there for a very long time. So you can compare tombstones of different locations and notice the rate of weathering. It's pretty interesting, actually. And here you can see these may be either newer than this tombstone, or this may have been more resistant to weathering, or in a climate where the weathering isn't as much of a factor as in this location. So it's interesting how you can compare tombstones and learn information about its rates of weathering. Here's a statue that has been weathered, and this is actually a picture of acid rain that had weathered and eroded away the face and the features of the statue. So what else affects the rate of weathering, or how fast this process can occur? Well, we have to look at the mineral composition that's making up that rock. If it's composed of soft minerals, then that's going to weather faster. If it's made of hard minerals, then it may be harder or more resistant to weathering. So that's it goes directly with the hardness of the rock and the rock's resistance to weathering. So these both will come into play when we look at weathering as a whole. In this picture, we have a nice waterfall over several layers of different rocks. So which rock is most resistant to weathering? So we're going to look for the picture of the rock that has been less carved out by the water. And you may notice that if you compare all the different rock layers, the top layer of dolostone is mostly still squared off. So we say that that is the most resistant to weathering in this rock outcrop. I'm going to remove that picture and show you again. See how it has the nice squareness to it still, where every other piece has the carvings. So that shows that it has been exposed to the weathering and it has been weathered. So what is the end product of weathering? Sediments. And we're going to stop there, and we're going to talk more about sediments and their role in weathering and erosion in our next video. Have a great day. Don't forget to get the notes down. See you next time.